Section 12.5, Triple Integrals, Video 3. In the previous two videos, we talked about evaluating a triple integral over a solid that was just a rectangular prism. That was easy to define because the x's are always between two constants, the y's are between two constants, and the z's are between two constants. But we're going to run across triple integrals where the solid over which we're integrating is not so nice and flat on each side. For example, there are going to be three types of regions that we're going to consider integrating over. We're going to call them type 1, 2, and 3. And just for clarification, the textbook uses the phrase regions. To me, a region is a two-dimensional surface, whereas a solid is a three-dimensional, solid. So I'll be saying the word solid interchangeably with the word region. But personally, when I say the word region, I usually refer to something in two dimensions. All right, so let's take a look at a type 1 solid. A type 1 solid is a solid that's bounded above and below by two surfaces defined by z equals u1 of xy, some function of xy, and above by z equals another function of xy. We'll call that u2. So in other words, we have some surface on top, and that surface is z equals u2 of xy, and it's bounded below by some other surface, so let's just see if I can sketch something here. Not the best surface I've ever drawn, but I'm not the best at drawing them. And the bottom surface is defined by another function u1 of xy. And we basically just connect and then project this down onto the xy plane. So basically it's like a cylinder where the tops and the bottoms are curvy and wavy. And if we project this straight down, then we get some sort of region. We'll call this region D. And by projection, I mean if you were to put a light source directly above it and all of the light rays went straight down, not out, but just straight down, then it would be the shadow that it casts on the xy plane. And then if we wanted to evaluate the triple integral over this region, let's call this, the solid. Let's call this solid E. I'll make it kind of a bold E to emphasize that it's more dimensional than this guy. If we wanted to evaluate the triple integral over this solid of some function f xyz dv, we could first integrate the function with respect to z, and the limits of integration would be the boundaries in the z direction. On the bottom it would be this function, on the top it would be that function. So u1 xy, u2 xy. Now, what about the dy and the dx? Well, this region may be pretty simple. It may be a rectangle, it may be something that's easy to define, or it may be pretty curvy. But we can think about integrating over this just as a general double integral. So double integral over the region that represents the projection of the solid onto the xy plane, dA. And then when we get to this double integral, we just treat it like we did in previous sections. So that's type 1, where the solid is defined by being between two surfaces of the form z equals u2 xy and z equals u1 xy. And then when we get to the double integral, we worry about what's going on down here. The type 2 solid is pretty much the same thing. The only difference is which way the two surfaces that we're trapping the solid between are oriented. For example, if they're functions of x and y, then we're talking about them from the z perspective. But we could have functions of x and z, or functions of y and z. For example, let's take a look at one that's a function of... Actually, before we get to that, let's be a little bit more focused on the d down here. Let's say that this d, this region down here, can be defined. I'm going to project this over to the x-axis. And let's just say that the interval on the x-axis is a to b. That's pretty convenient. And it's kind of twisted the way it's oriented. I don't know what genius decided to shoot the x-axis out in this direction, but I wasn't there when they had that discussion. But if we were to just focus on this, and I'm going to draw a real rough sketch of it here. Here's the x-axis, here's the y-axis. Here's the region over which we're integrating. And we've already said that this is between A and B on the x-axis. If that region is defined on the bottom by, on the top, excuse me, by y equals, we're using h, I'm trying to be consistent with the book, y equals h2 of x, so that would be the top half, the curve on the top, and the curve on the bottom is y equals h1 of x, then we could evaluate the integral, the double integral over the region as, remember we've already got this integral in the middle, so u1 x comma y, u2 x comma y. I'm just going to write f for brevity, knowing that it means f of x, y, z. We could do the double integral over this region by integrating with respect to y first, because the boundaries, because the equations defining the top and bottom of the region are functions of x. So integrate from h1x to h2x dy, and then the dx would just be from a to b. I know it sounds kind of complicated, but really all you're doing is you're doing one integral with respect to the variable that's equal to the function of the other two first. So in this case, the top and bottom are defined as surfaces and as functions of x and y, so we integrate with respect to z first. Then when you push it down here to the xy plane and you look at it as a double integral, you can either integrate it dy if the tops and bottoms are functions of x, and then integrate with respect to x across an interval of constants, or the other way around if your region, well, let's save that for the next video. There are two other types of regions, and in the next video I'll just briefly describe them. They're very similar. The only difference is who gets to be the predominant variable, who's a function of the other two, and you integrate with respect to that variable first.